Good afternoon. It gives me a great pleasure to be here after 50 years. And what I would like to do today is to give some recent advances in interpreting deep marine deposits. The deep sea exploration began 150 years ago when the Royal Navy launched HMS Challenger, and they were the one who discovered the deepest part of the ocean that we call Challenger Deep, which is 11 kilometers deep in the Mariana Trench near Guam. So, as Mitch mentioned, I published this book a couple of months ago. My focus during the past 50 years is process sedimentology and physical oceanography. And this book is all about that. The title is Mass Transport, Gravity Flows, and Bottom Currents, Downslope and Along Slope Processes and Deposits. The picture you see on the cover shows the downslope process intersecting with along slope process. How did I arrive here? I have to go through a chain of events that took place during the past 56 years so that you'll have a better understanding of the history behind this talk, this book. As Mitch mentioned, one of my article came out just 2 days ago. The word serendipity comes to my mind, fortunate coincidence. So I was born in a small town in the southeastern coast in a state called Tamil Nadu, and I attended the Annamala University there nearby. I got my bachelor degree in 65. Then I moved across the country to IIT Bombay, where I got my master's degree in applied geology in 68. I must mention one thing about IITs. They are one of the top institutions in the country for science and engineering. This is the first event in my life, probably the life-changing event. After I got my bachelor degree, I took a science teaching job in this little high school. Then the head of the department, Professor Muthuswamy, asked me to come to his office. I went in. He said, quit the job and go to IIT Bombay, pursue your studies. You have a tremendous potential to become a successful geologist. I did. I went to IIT Bombay. I was the top student. They gave me a medal. They trained me in petroleum engineering, sedimentology, soil mechanics. That YNGC is the Oil and Natural Gas Corporation. They trained me in the field, in the office, and so on. My professor was a Parthasarathi. He studied at Imperial College. He got his PhD in engineering geology. So my background is more towards engineering geology than pure geology. Then I came to Ohio University. I studied under Dr. Fisher. I already mentioned a lot about him in the email I sent to you all. And he got his PhD in Cornell, 1952. He was the chair, he was the associate dean. He worked for Gulf Oil in South America. And he got samples for me from Texaco Company. This is dealing with the Simpson sandstone in Oklahoma. He has been everything to me when I was at Ohio. He was my science advisor, social advisor, financial advisor, everything you can think of. So I set up this endowment for $50,000. The way it is worked out is I will pay 25,000, ExxonMobil will pay 25,000. I made a 4-year commitment. I already paid this year's pay, and I'll be completing this in 3 years. The purpose of this endowment is to fund research by faculty and students. Then I went to Tennessee. I studied under Kenneth Walker. He has a PhD from Yale, very pragmatic, hardworking professor. He put me to work on the middle division of the Appalachians. The basin I worked is the Sevier Basin. This is the one I coming up the model. I found out it's a deep water basin. Before I worked on it, we didn't know anything about it, but it was a critical piece of the puzzle in the plate tectonics domain. So when I came up with this idea, and it had turbidite, contourite, debris, and soft sediment deformation, rapid subsidence. This is one of the pictures of debris you see here. And they were drilling the DSDP site 262 in the Timor Trough. And the results they published is very much like what I was finding. So I proposed that the severe basin was a 4D basin. When I published in Geology, there were a lot of commotion, controversy. Now it is an accepted model. Then the head of the department in Tennessee, Garrett Briggs, he called Mobile Research in Dallas, and he asked them to give me an interview. They did. I attended the interview in this first building. They had three research centers in Mobile, in Dallas, and after the interview they hired me. The advantage of the job is it was research, teaching, travel, so everything I wanted in my life they gave it to me. The other advantage, Mobil was the second largest company at the time in the world next to Exxon. So they enabled me to travel all around the world. For the first project I did was went to New Zealand, studied the rainforest and their capacity to generate oil from trees. May sound strange, but it is true. I published a paper in the AAPG Bulletin in '85, and even today, after 35 years, that is one of the most cited papers in petroleum geochemistry. So as you can see, the building is not very impressive, but it was functional. But because Mobil was the second largest company, they wanted to expand the research. So they wanted to put a lot of money. They hired I.M. Pei. He was one of the most recognized, renowned architect at the time. He was the one who built the Louvre Pyramid in Paris, France, and he also built this Bank of China in Hong Kong. There is a YouTube documentary on him. Anyway, he was the one who built the Mobile Research Center in Dallas. I spent most of my career in that building. I studied the Washita Flats, North Sea, Norwegian Sea in Nigeria. They're all deep water reservoirs. Then I moved to this research, and from there I studied Gulf of Mexico, France, Ecuador, Gabon, Brazil. Because of all that experience, when I retired, PetroChina hired me as a consultant. This is one of the group photograph. I gave a deep water workshop in Beijing. As you can see, I am the only one wearing a white sneakers, the group photo. Then I gave another workshop for the Petroleum University in Qingdao. There's I'm sitting there, the red dot. So this all led to 380 publications, 3 books, and 2 of them have been already translated into Chinese. This is the book I'm talking about. This is the basis of the talk I'm going to give. So this is where the talk begins. I have selected 11 topics. The first one is the downslope processes. When I mention deep marine, I mean anything deeper than the continental margin, continental slope. That's shelf edge is about 200 meters in today's terminology. There are 4 major processes: slide, slump, debris flow, and turbidity currents. The first 3 are together called mass transport processes, and the deposits are called mass transport deposits, MTD. Of these, the first 3 are more important than turbidity currents. So how do you recognize slide, the first one? We have to deal with the soil mechanics and slope stability. The expression F is the factor of safety. When the driving force exceeds the resisting force, then the soil column peels off and move intact as a coherent body along a glide plane. And how do you recognize that in the core? This is the sketch of a core from the North Sea. As you look at the bottom of the sand, you see the shear zone along a glide plane. So how the real rock look like? This is how the real rock look like. You can see the shearing at the base. can see the sand injection. So that's the typical of a slide in the rock. And so this is a small scale. So how does it look in a larger scale? This is how it looks. This is a large slide in Antarctica. This is about 50-meter thick and it is moving along a glide plane. There's a human being for scale. So you need rocks to identify slide. But there are publications, they say they use the word slide for images like this. Here you cannot tell what is the bottom is doing. You need rocks, you need core. So we should use the word mass transport deposits, a general term rather than a very precise term slide. The next slump. There are two types, tectonic and sedimentary. The sedimentary type is the one that is sandwiched between undeformed units, slump in the middle. There's a beautiful example near San Diego. This is the upper undeformed sandstone. The lower one is the deformed sandstone. If you go to La Jolla, take a look at it. It's a beautiful one. The next point is rheology. This is the fluid mechanics, and this is the stress-strain relationship. If you apply stress to a fluid and if it deforms, it's Newtonian. And if it waits until the yield strength is reached, then deforms, it's big and plastic. Then you apply the Reynolds number. If it is more than 2000, it is turbulent, which is turbidity current. If it is less than 500, it's laminar, that's debris flow. So this is all theoretical. Now we can actually see these things in a flume. Let's go to University of Minnesota, St. Anthony Falls Laboratory. We put slurry into the head tank, and when the flow comes down, this is what you see. A basal, laminar, sandy debris flow, and upper turbulent turbidity currents. So you can see all this in real life. So what happened? Some people combined these two into one, called it high density turbidity current. The problem is, if you plot the sediment concentration, the high density turbidity current overlaps debris flows. So that's confusing. So I wrote a paper called High Density Turbidity Currents, Are They Sandy Debris Flows? It is published in Journal of Sedimentary Research, and it was controversial. Then they took a survey, and after 6 years, they found out that is one single most cited article in Journal of Sedimentary Research, Sedimentology, and Sedimentary Geology. So how do you recognize debris flows? This is your core. This is the clast floating in the sand. I just projected it to show you how it might look like in real life. The long axis of the clast align parallel to the bedding plane. This we call planar fabric. That means it's formed by laminar flow, meaning it's a debris flow. This is how it looks like in the outcrop. If you go to Los Angeles next time, take a drive to Dana Point. This is what you will see. The next, turbulent turbidity current. This is a flume picture, the turbidity current coming towards you. It's highly turbulent. When they deposit from suspension, they form beautiful normal grading. This is how it looks in outcrops. If you go to Spain, take a drive to Zumaya Beach, this is what you'll see. This is Dr. Arnold Baumer. He did his PhD in 1962. He studied the unknown sandstone in southern France, and he came up with this idea that a typical turbidite bed is composed of A, B, C, D, E, and E, 5 divisions. After he published, there were several papers questioning his model, that the Baumer A division can be formed by debris flow, grain flow, and other flows. There are others started questioning the transition from TA to TB because nobody could reproduce this in flumes. So all this argument was going on theoretical basis. I was working for Mobile. I thought the best thing to do is to go to southern France, re-examine the same rocks that he did, see why all this controversy. So 3 people from Mobile went to Piracava in southern France. This is the city of Nice. and this is Mediterranean Sea. This is the area where we studied, where Bama also studied. I'll show you just three or four examples. And these are all published in Earth Science Reviews. The title of the paper is called 10 Turbidite Myths. It's a very controversial paper. This is one of the beds he studied. If you look, you can see the inverse grading, pockets of gravel, floating clast. These are all can be explained by debris flows, not turbidity currents. Then if you look at this, there are double mud layers. These are deposited by tidal currents, not turbidity currents, but he didn't mention them. There are sigmoidal crossbedding that he didn't mention. This is how the sigmoidal crossbedding look like. This is part of the tidal bundles that he didn't mention. Why? Because at the time he published 1962, the concept of double mud layers, sigmoidal crossbedding, they didn't exist. They were published in the 1980s, 20 years after he did his PhD. So you can't blame him. But at the same time, the Bama sequence, which is very popular in textbooks and so on, it is obsolete. The next point is the water masses flowing all over the place. I'll just show two examples. One is Mozambique, the other one is Atlantic. And we go to the Mozambique. This is the underwater photograph showing ripples. And this is how the ripples in the Atlantic shows. That is studied by Hollister, Columbia. Then when you come to the Gulf of Mexico, there is the wind-driven loop current. And this loop current, underwater photograph shows they form ripples. And when you look at the core I studied, they show ripples. So we have ripples in deep water all over the place. They are found by different processes like contour currents, tidal currents, and so on. You can recognize them today because we know the answer. But if they occur in the ancient, you cannot. We don't have the criteria. The next point is submarine fans. Shepard and his colleagues measured currents going up and down the canyon in deep water, even at 4,000 meters water deep. So he wanted to know why the currents flow upslope in submarine canyons. So he matched the tidal chart for each canyon. They match perfectly, meaning the tides control the currents. So using that knowledge, I was looking at core from the EDAP area in Nigeria. They see the double mud layers. So I used the concept of Visser published and suggested that these deep water sequences with double mud layers were formed by deep water tidal currents. This is published in Marine and Petroleum Geology. Then the internal waves, you see them on the satellite images. This is from the Andaman Sea. We also recognize them in deep water, 1,500-meter water deep. This is in the Horizon Guyot. Using all that, I published this model in the APG Bulletin where the internal waves comes and here's the continental margin and also reworked the Guyot. This is the actual example published by Lonsdale and others. The next one, this is the one appeared on the cover of my book. There are currents coming down slope and they're intersected by along slope currents. This is a genuine hybrid flows. But there are people, some researchers suggested that when the gravity flows go down slope, they go through flow transformation and they call that hybrid flows. This is confusing because they misapplied the term hybrid. Whenever there is a new term we apply in geology, we should go to etymology, try to understand where the term comes from. In this case, when you want to use the word hybrid, go to Cambridge Dictionary. If you don't like that, go to Oxford Dictionary. They all say the same thing. It is derived from the Latin word hybrida. That means you take two different species, you merge, and you form a hybrid species. In animals, for example, you take a horse and it mates with a donkey and it generates mule. That's a hybrid species. In this case, you take a debris flow and it moves downslope and it transforms into turbidity currents. That's flow transformation. This is exactly what I showed you and that flume photograph from University of Minnesota. So this is not this. In fact, flow transformation is just the opposite of this. Here we start with two species, end up with one. Here we start with one, end up with two. So words do matter. This is the deflection of sediment plume. This is the normal time in the Washington state. This is the Elba River, and they deposit a little bit of deltas. In 2012, they removed the dam, and it resulted in release of 20 million tons of sediment. So this is the sediment coming out. Normally, it should form a delta, or it go down slow, but it's taking a 90-degree turn here. Why? If you look at the Strait of Juan de Fuca, if you study the wind forcing, and the wind forcing causes the sediment to turn, go this way. Why this is important? If you do a rock study in say in the Jurassic, if it occurred in the Jurassic, you wouldn't have a clue that the source was here. There was a 90-degree turn if you do the paleocurrent analysis. So we have to understand these anomalies to understand the ancient. The last point is the tsunami. This is the Lituya Bay in Alaska in 1958. There was a large tsunami from 524 meters tall tsunami. If you take that tsunami wave and put it in Chicago, this is the Sears Tower, it will topple the TV antenna. So such a huge wave formed by tsunamis. So this kind of information I published in the Journal of Sedimentary Research. I proposed this model. This is you form an undersea earthquake, it generates tsunami waves, they drop large boulders, exotic boulders, and then the tsunami waves retreat, leaving the boulders, and they also form deep water. That's the model I proposed. So this is the reality. This is the Tongatupu Island in Southwest Pacific. This is the large exotic boulder. This is about 9 meters in height. So what if it occurs in the Jurassic? If it is subsurface, there is no way you can identify this. So I published these problems in the Natural Hazards, published in 2012. So how do we solve these problems? Uniformitarianism. The present is the key to the past. The more we know about the present, the better we are in interpreting the past. So what I have learned, soil mechanics and fluid mechanics are the basics to understand deep marine processes. That's not the only one, that's one of the basic information. High density turbidity currents are debris flows. Balmer sequence is obsolete. Deep marine ripples, we need criteria. Double mud layers, its tidal origin. Hybrid flows are not, they are not flow transformation. They're totally different. Deflecting plumes are caused by wind forcing. Tsunamis, we don't have criteria. Uniformitarianism is a solution. So the deep marine system is still a new frontier for research. If you're looking for a project, do a master's degree or PhD research, or even other research, there's tremendous potential in the deep marine systems. So I'd like to thank all these people and organizations. The first one is my wife. We have been married for 45 years. Ever since, she has been controlling my manuscript quality. Whenever I want to publish something, she'll read and find out all kind of mistakes. Only when she okays, then I will submit the manuscript. This is Mayola, my manager, friend, mentor in mobile and mobile company. Today, Professor Alicia Stigl, I give this talk mainly because of her. Otherwise, I would not be giving this talk. Alumni Symposium participants who listen to this talk, thank you all. I'll finish off with 2 slides. My hobby is taking pictures of unusual rocks and publish them on the covers of international journals. This is just 3 of them. This is the Pulpit Rock in Norway. It's a huge cliff. If you have watched the movie Fallout, the last installment of Mission Impossible series, that movie was shot on that cliff where Tom Cruise was fighting the bad guy and finally killed him, thank God. This is the shot I took from Lee River in southern China. These are limestone karst. This is a huge granitic boulder. There's a man sitting here for scale. This is near Chennai, India. So we have sedimentary rocks, we have igneous rocks. Here comes the metamorphic rocks. This is the Makrana marble in northern India. And with that, let me end this talk. Thank you.
Thanks a lot, Dr. Shanmugam. That was fantastic. And I think we have a few questions, and I'll ask, let's start with Greg Pavlin, if you want to unmute.
Yeah, Dr. Shanmugam, I want to thank you for your presentation, along with that of your spouse and your career, which is very impressive. You're definitely an overachiever. I was just wondering why you picked Ohio U for your second master's. I mean, you could have picked any place. Why did you pick Ohio U?
Yeah, that's a very good question. That is the only one that gave me assistantship.
What were they thinking?
What was that?
What were the other schools thinking? They should have.
The other schools I got for example, I applied to several schools. For example, University of California, Berkeley, University of Wisconsin-Madison. They all gave me admissions, but they did not give me scholarship. See, that was the key. I could not come to this country without scholarship. That was the key. But even Ohio, they gave me only one half assistantship. They wrote to me very clearly, we don't know what kind of English knowledge you have. In order to give you full assistantship, we should confirm ourselves that you have a good knowledge of English, that you can teach English. So I understand their concerns. That was the reason I didn't get too many offers. But
Do you think
after the first year at Ohio, they gave me full assistantship.
Very good, sir. Thank you.
Thanks, Greg. I think Pat Jackson, did you have a question? I thought I saw in the chat. Well,
I don't think I put a question in the chat, but of all these different depositional environments that you've described in the deep water, which one's the most profitable? Is it fields in the turbidity currents?
No. Let me expand that question, that answer.
Okay.
What happened was during the last 50, 60 years, when the concept of turbidity currents came into existence, let's say 50, 60 years ago, up to that point, people were very skeptical of any process in the deep sea. The old books, if you see, they were all in the deep sea deposit, mainly mud. There were no sands. So the turbidity current concept came into existence in the 50s and so on. That allowed to put sand in the deep sea. So they took on very fast. So everybody liked the turbidity current concept. Then what happened was they were become overzealous. They went to the other extreme. They started calling everything a turbidite. If you see a conglomerate in the deep sea sequence, they would call it a high density turbidite. As I mentioned earlier, that's a misnomer. There is no such thing called high density turbidity currents. It's essentially a debris flow. So to answer your question, most of the rocks I described from the deep sea, they are mainly composed of debris flow deposits. But the managers in oil company, they are very afraid of using the word debris flows because it has a negative connotation. It has a high mud matrix and so on. But that's not true. But they have this fear that debris flows are bad for reservoirs. But that's not true.
thank you. I think we have time for another question. I think we're trying to find it, but I think it was Wolf Clifton had a question. If you want to unmute.
Yes, that's right. My question really tails on the end of the last one. Is the concept of the Buma sequence still useful, at least as a simplified model in sedimentology and stratigraphy, or does it need to be completely discarded or replaced?
Yeah, it has to be discarded.
Okay.
Let me expand that. It's a very blunt answer. The problem with Obama, it was a reasonable one in 1962. At that time, we didn't know much about deep water processes. Since then, we have learned a great deal. When you know so much about modern deep sea processes, the sequence that was proposed 1962, it becomes obsolete. Like I showed you from the rocks I went and re-examined. They're totally different beasts than what he described. So you can't hang on to this model, although it's a popular model. It's all in all the textbooks and so on. It will take some time, but we have to do it.
Okay.